Welcome to the week 3 of the live interaction session of the fundamentals of micro and nanofabrication. The course instructor is Professor Sushovan Avasthi and Professor Sankar Selvaraja from ISC Bangalore. I am the PMRF teaching assistant Vikas Pandey from IIT Jodhpur. This is a brief about me. I am PhD scholar at IIT Jodhpur. Uh, the academic backgrounds are MTech in VLSI and BTech in Electronics and Communication. I work in field of HEMT, sensors and IoT. I have interest in machine learning, microfabrication, and additive manufacturing. The class link remains the same throughout this course, and all the recordings will be available on the YouTube channel mentioned here. You can take a screenshot. Anyway, these slides will be available in the course forum also. And for further clarification or any details, you can check my profile as well as you can write a mail to me. Okay. So before starting, uh, today we are going to discuss additive manufacturing, native films, and we will be discussing some questions based on that also. So before starting, if you have any question related to the topics covered in this week, you can ask, or even we can discuss at the end of the session. Any questions?
We'll discuss at the end of the session, sir. Is that okay?
Yeah, sure. Not an issue. Yeah. So throughout the session, I will not be able to check the messages. So feel free to unmute yourself and ask questions. Wherever you have doubts, you can interrupt me, not an issue. Okay. And please be interactive. You can ask and interact as much as possible. Okay. So first we will be covering the summary of the things that has been covered, although it is already there in the lectures. We'll just summarize all the things that has been covered in this week, and then we will go to the questions based on that. Okay. So starting with, remember in the previous week we have covered diffusion and ion implantation. Okay. So we saw that ion implantation is better than diffusion because it here we can have better control of the profile. We can go for fixed area doping and all these things. But there are some non-idealities associated with this ion implantation, like backscattering, where the lighter ions, which are like boron and these things, can scatter instead of penetrating inside the silicon. They might get reflected. Okay, and that causes something called a front biased profile. Okay, the front biased profile will look like on the top there will be less, like the one with lower energy uh, ions, lighter ions with lower energy may backscatter. So on the top surface there can be some lower number of doping compared to what we were uh, thinking or what we were planning for. Or in case of heavier ions, it will be the opposite, that is rear biased profile. So in the no, like if we see this is the depth, if this is the surface, 0 I am taking. So the rear side, that is the back side, inside, what we were expecting, there will be lesser number of ions compared to on this what we were expecting. And the effect of that will be asymmetric profile, which is called by difference in ion mass and energy. Okay. Then successive implantation, because there might not be the case that we are implanting with only one material like boron. Okay, it might happen that we are first trying to make it as p type, and then we are trying to make it as, like, some part of it we are again converting into n type, n plus. Okay, so successive implantation at different energy, because we want different penetration depth and all. This can create custom, using successive implantation, we can create custom doping profiles. Okay. In this case, unlike the diffusion and implantation, the previous, like in case of diffusion, if we are going for further diffusion, the earlier doping will get disturbed. Or in case of ion implantation, if we first do some doping and then we are doing successive so ion implantation, then in that case also the earlier profile will get disturbed. But the challenge with a successive implantation is that we don't have to disturb the previous profile. Like if we have a wafer, let's say this is the top, and we have doped this area with P, we have made it P type. Now we want some discrete areas to be N type. Okay, so suppose we did ion implantation and we made this whole area as P type first. Now using a mask, we want to just make this N type. But while making this N type, we don't want the previous profile, that is the P type that we had made, to be disturbed. And how is it done? It is done by using the method of first doing a low energy implantation and then followed by high energy to create a uniform profile without disturbing the previous implantation. And then one problem that occurs with this implantation is that there will be damage. That is the most. Are you uh, are you able to hear me, everyone?
Yes, sir. We can.
Okay. Yeah. So the one problem with ion implantation is that it creates surface imperfections or damages the surface. Okay. So we have to repair that implantation damage. Okay. As collision will occur, certainly it is not pinpointed at interlattice species. So there will certainly be some collision. Okay. And create this will create disoriented regions in the silicon lattice. Like if you see, we are looking, okay, this resolution has gone down. Not an issue. Are you able to see this picture? These two?
Yes, yes.
Yes, sir.
Okay. So, like ideally, the lattice should be perfect, but when we are doping, there will be some collision, and that will create some disoriented region. Like the positions will change, and the crystal itself can have some disorientation. Okay, as well as if we are going for higher doses, like we are continuously implanting for a longer period of time, that can even create a amorphous silicon layer on the top. All the crystals get disoriented, and this needs to be repaired since the top layer is the one where all the devices are made. Top, we are doing most of the things on the top of the silicon. Okay, so we need to repair damage and also activate the dopants. Activate the dopants means that they should also occupy proper position in the crystal structure. Okay, so one way is solid phase epitaxy, where it is done at a low temperature, and epitaxy, like we will also be covered in CVD case. Okay, where the orientation is not disturbed. Okay, and the second way is RTA, or rapid thermal annealing. That is, we are hitting it at a very high temperature so that the crystal orients itself, and we repair the damages that has happened due to the ion implantation. So RTA is one of the most common ways how diffusion or this ion implantation damage can be repaired. Okay, so let's see a comparison between diffusion and ion implantation. These are the two types we had seen. Okay, diffusion is a high temperature process, whereas ion implantation is a low temperature, or we can say room temperature process, and is ion implantation more precise and controlled. In case of diffusion, it creates isotropic dopant profile. The doping will be uniform in all the type, all the way. We are not controlling the direction of doping. Whereas in case of ion implantation, it is anisotropic profile. And this is very useful in case of small devices. When we are going for scaling down the devices, we are going for nanometer range and all. We cannot rely on diffusion because here the profile will be uniform, and we want things to be in one direction, or say two directions only, as per our need. So ion implantation will be better in that case. In case of diffusion, we are using hard masks like SiO2 and silicon nitride. In case of ion implantation, a simple photoresist mask can also work. Although some soft mask of SiO2 is also used in some cases, but mostly photoresist will work fine. But in case of diffusion, we have one advantage, that is it can be used for batch processing. Like large scale production, for large scale production, diffusion is much better. Whereas in case of ion implantation, the quality is good, but it takes time. It is very time taking process. One by one, you have to, like, you cannot do a batch processing. There is limit how much you can put, like 3 4 wafers, that much, or 10 maximum. But in case of diffusion, we can process 100 or 1000 wafers at once. Okay, so this is ion implantation has the limitation that it cannot be used for batch processing for large scale production, whereas diffusion can be used for large scale production. But in case of ion implantation, we are getting more precise control of doping, as well as there is anisotropic profile. So for small devices, which like nowadays we are trying smaller and smaller devices, so in that case ion implantation will be a better option. Fine. Anything till here?
Nothing, sir, but I have one query related to diffusion and ion plantation. Can we ask right now, or can we
Yes, yes,
cover it later?
yes, you
We
can
can
ask.
ask right now.
Yeah.
Okay. See, my question is whether any devices follow both the options like diffusion and ion implantation, or only any one is always followed for the device.
No, it depends on your purpose. It can be that first you are going for diffusion, like you have to create, say, you have some big areas to be diffused. Okay, and so you might go for diffusion, and then you have small precise areas later on the in the fabrication step where you want some precise doping. Okay, in that case you can go for ion implantation. So it is uh, as per your need, and like as per the how well you can optimize. Since if you are going for diffusion, that is a low cost process. If you are going for fabric microfabrication, certainly cost is also a important parameter, right? So if you have cost constraint, as well as you don't have that stringent condition of doping that you need, you can go for diffusion. And in the processes where you need very stringent condition, and the doping profile has to be very well maintained and all, there you can go for ion implantation, but certainly it will be time taking as well as high cost. Okay, so there can be a possibility that if you have both the facilities, and the part where you like you don't bother about the precise precision, there you can go for diffusion, and that part where that process where you want very precise one, you can go for ion implantation. So it is a mix, or whatever facility you have. I hope I answered it right.
Yes, sir. Yes, sir. Thank you. Yeah.
Okay. Yeah.
And
Any?
one more
Yeah.
question
Yes.
related to diffusion and this one. Say you have a wafer, so we follow
Hmm.
diffusion or ion implantation, whatever it is. So is there
Yes.
any visual change after this process? Can we able to see it like
Uh,
means with our naked eye? I mean to say.
no, not with naked eyes. I think in the previous lecture, at the end, we covered some methods. Like remember four probe and two probe method. Four probe, hot probe method, and there are some two probe method and these things. So
Okay.
what this characterization technique basically does is that there you check the resistivity or conductivity in a sense, right? You are putting probes, and so intrinsic or the basic silicon that you bought will have some resistivity, and then when you are checking the resistivity after doping, there will be change. Based on this, we understand visually. uh, in case of diffusion, there is no change. It will look exactly the same.
Okay, sir. Thank you.
Yeah. Okay. Any other questions from anyone? Okay, so let's move forward. Now we are coming to something. These are all additive processings. Okay, additive means where we are putting something on our wafer. Like we started with in the first week, we were talking about silicon, pure silicon, how it will be made and all. Now on it, we have to put some things. So one thing is that we are putting some molecules or some atoms inside it. That is in sense of doping. Now the next thing is growth. Like we are growing some oxide over it. Okay, native oxide. That is why it is called native oxide, because we are not bringing anything from outside. If we have a silicon wafer, okay, we are using this silicon wafer only to create a layer of SiO2 here. So in a sense, we are oxidizing the silicon on the top and converting it into SiO2. Later on, we will even study that we can even deposit it. So there is difference between growth and deposition. Growth is when we are using the same material, like we are using the silicon itself to make the SiO2. That is growth. And it is called as native oxide because it is using silicon. Like natively it is growing. Okay. Are directly grown from the wafer. So wafer is the precursor. Precursor means the uh, starting material. Okay. It is one of the most important insulator in case of semiconductor fabrication. It has a lot of applications. Wherever we are going for microfabrication, silicon dioxide is a very important part, where it plays a very important role. First and the foremost and most common one is the gate oxide in FET. So anyone knows how a FET looks like? I think most of you. Yeah,
What's your question? I didn't understand.
FET, field effect transistor. You are aware with the structure of FET?
No, sir. I never saw it, but
Okay,
I know I read about this
right.
FETs.
Okay. Yeah, anyone? I think there is some. Yeah, Maya Manoj, are you there? Hello. Yeah,
Yes,
are you aware of field effect transistors?
so I have studied PET in my PG. I didn't see, basically, I didn't see any PET.
Okay. Okay. So I will just draw a small structure. I think most of you are familiar with it. Like we have, say, this one is source, this one is drain. Okay, we have electrodes here, okay, and then we have some dielectric here, and on top of it we have electrode, that is gate. Fine. So this dielectric that we are using, I think I should use some other color. The dielectric that is being used here, that is in general silicon oxide, and that is the one of the key applications of using SiO2. Nowadays, things like hafnium oxide are also used. There are a lot of dielectric being used, but yet all of them will have some layer of SiO2 because that has very good adhesion over it. Okay, clear? So first one is gate oxide. Second is we are using cleaning oxide, cleaning process also. We were using SiO2 that was being removed using HF. Remember in the first week we covered that HF dip was used to remove the native SiO2. Then there is masking oxides. In case of diffusion as well as ion implantation, SiO2 is used as masking, that is, it will cover the area in which we don't want the diffusion to occur. Okay. Then filled oxides for device insulation. Suppose you are making electrode, you have deposited metal. On top of it, the areas where you don't want it to be exposed, there also filled oxides are used. In all these cases, it's not necessary that it will be a native oxide. It can even be deposited. But we are talking about the importance of silicon dioxide here, okay? Then there can be insulating layer between metal layers because we will do multiple layers of metals will be kept, like one layer, and then interconnects will be there. So to separate them, that there also SiO2 is used. So it has a lot of application in semiconductor fabrication, and that is why we are first covering how it is grown, and later on in case of CVD and PVD, next 2 weeks, in that also you will see that some deposition techniques for SiO2 will be covered. Okay, so when we are talking about growth, what is the mechanism of growth? There can be two ways in which this can be grown. One is dry oxidation, the other one is wet oxidation. In case of dry oxidation, oxygen gas is used, and this produces very high quality oxide but has a slower growth rate. So Si is there, O2, and then we get SiO2. Okay, simple oxygen, but this process takes place at very high temperature. The temperature is generally in range of 1000 degrees, 800 to 1000 degrees Celsius. Okay. The second way is wet oxidation, where H2O vapors are used. In this case, hydrogen will be released as a byproduct, Si plus H2O, okay, Si, Si plus 2H2O, and it will give us SiO2 plus 2H2. Okay, this this has a faster growth rate and it is slightly lower in quality. Why the quality is lower? Because when the hydrogen is formed, it will try to escape from it, and that is why sorry, that is why the quality is a bit lower. Okay, so this whole growth process is presented in a model called as Deal group model. It describes how the SiO2 grows on the silicon. So first, before going into the equations and all, let's understand that if this is the wafer, uh, let's say this is, we are starting with here. Are you able to see my marking where I am putting?
Yes, sir. Yes.
Okay. So this is the top surface where we are starting. We have inverted the wafer, and like we are saying this is the top, and going inwards we are going towards the bottom. Okay, going forward we are going towards the bottom. So this area is the gas. It can be O2 or H2O. Okay, so these molecules will go inside the wafer. Now let me put some color. Okay, they will move inside the wafer and do the reaction Si plus O2 or Si plus H2O. That reaction will occur and SiO2 will be formed. So the top layer is converted to SiO2. Then the next batch of the precursor oxide, precursor gases will come, and then they will have to diffuse inside. They will go inside and then they do the reaction, and this, as such, the process will continue. So there are actually two part. Uh, like starting of the reaction will be gas concentration dependent. How much gas is available on the top, that will lead to the reaction. But as we move forward, this reaction will become more of yeah, this reaction will become more of diffusion dependent. That means how much of these spaces, oxygen or H2O, diffuse inside Si, uh, not SiO2, because the top layer will become SiO2. Okay, that will define the amount of like rate of reaction, how fast it is working. So the like if you are not going too much into the equations and all, let's understand simply that it is the initial growth rate is reaction limited. So it is simply the reaction, how fast the reaction between O2 and Si will take place. That is simply the first part. The latter part is diffusion limited. How fast these spaces will diffuse in. And here you see H2O and O2. Yes. Can anyone tell which of these molecules will be bigger in size? H2O or O2?
Just a wild guess, oxygen, because I
Yes.
studied this in maybe high school or something. Yeah.
Yeah. Yes. Anyone else? Anupam? Or yeah, Maya Manoj?
So oxygen is bigger than water.
Oxygen is bigger or smaller? Yeah, your sound is not very clear. Can you speak again? Hello?
Oxygen is bigger than water.
Yeah, oxygen is bigger than water molecule because oxygen uh, molecule is big, and hydrogen we know that it is the smallest atom. Okay, so one oxygen and two hydrogen, so overall it will be smaller compared to two oxygen atoms. Okay, so now you will understand why we say that wet oxidation is faster, because this molecule is smaller, so it is able to diffuse well compared to O2. Its diffusion rate is higher. Okay, so the like it can be represented in two ways. Like thickness of oxide is dependent on B upon A to time, where when it is linear growth region, B and A are rate constants. Okay, and then when we are talking about the parabolic growth region, there it is under root BT. So let's not go much into equations, that has already been covered. Okay, so just understand that at first it is on the surface, so it is reaction limited. Later on, it is diffusion limited. Okay, so at first, this area, okay, it is reaction limited. And later on, when we have this red is the original plot. So it is saying that approximately after 30 nanometer, we will see the linear region or the diffusion limited growth. Okay. Then there is something called as Pilling Bedworth ratio. Okay. This is again if we do the calculation uh, of the molecule size of the molecule. If we put the SI, what is the mass of SI? Molecular mass of SI silicon. Is anyone?
No.
Okay, let's forget about molecular masses. Everything I am putting here only. Okay. So if we simply say that the molar volume, that is the volume of silicon is 12.4 centimeter cube per mole. Okay. The same number of molecules of SiO2 will with 27 point uh, will have a volume of 27.19 centimeter cube. Okay. So if you compare this, you will see that the ratio is something like if we divide 27.19 by 12.4. Okay. So how much is the value? Anyone? Yes, anyone?
So
It's almost 1 by 50, sir. 1 by 0
Uh,
0.5.
no, 1 by 0.5, I didn't. Like, let's talk directly in decimals. How much? Yes, Manu, Maya Manoj, you are also saying something.
so 2.2.
Yeah, it
2.2.
is approximately 2.19. Okay. So, both like fraction also, it's fine. But to give the perspective, for one, uh, like 1 micrometer thickness of silicon, we will get 2.19 micrometer SiO2 when we are talking in the sense of thickness of growth. Okay, because oxygen is coming and this SiO2 that is forming is occupying more volume. Okay, so we can say consuming 1 micrometer of silicon will give us 2.19 micrometer of SiO2, or in simple terms, it is given in the ratio of 45%, like whatever SiO2 we are making. Okay, for that 45% of volume will come from Si and 55% of volume will be extra. Okay, so consuming this much of silicon, so this if this was the original silicon layer, this was the top layer, doing the oxidation will give us this whole amount of SiO2. Fine. Any questions till here? Oh, so how this oxidation is done? Oxygen has to be flown or H2O has to be flown at high temperature, 900 to 1000 degrees Celsius. Okay, but they can be done in two kind of setups. One is horizontal, other one is vertical setup. So in case of horizontal setup, if you see the furnace like this, these are the wafers. These are silicon wafers, and they are stacked in the vertical section. And these these are heaters which will heat the whole thing, and continuously the oxygen or H2O is flown. Okay. In case of dry oxidation, oxygen, nitrogen will be flown. nitrogen will not do anything. It will just uh, assist the flow, because complete oxygen will actually be wasted. So we just put that much what we need. In case of wet oxidation, it is simply uh, water is kept, and the air, nitrogen, is flown through it, like bubbled through it. So it gets wet and it carries H2O with it. Second way is this inlet setup will be similar, but here the wafers are kept stacked in vertical position. So it can be horizontal or vertical tubes. Okay. In all this, we cannot use simple plastic or glass. So quartz, all the equipment, like even the tray on which you will keep everything stacked, that is made up of quartz that can resist this much of temperature. As well as some baffle is used to reduce the heat loss. Okay, as we are hitting this, like circular ring kind of heaters are used, it might not be uniform. So some hydrogen baffles are used that will heat up. Okay, and continue even if you are not doing any oxidation at that time. Also, nitrogen will be kept flowing. Nitrogen or argon is rarely used, but mostly nitrogen will be kept flowing, so that there is no contamination. We have seen that contamination is a big issue in case of microfabrication. Okay, so to reduce contamination, there is always a flow of gas in the oxidation furnace. Okay, any questions still here? Okay, let's move to the next one. So how, uh, like, we have seen the setup, we know how it is done, but what are the steps that we follow to do this? So first we'll start with RCA clean. This we have already studied. Okay, then in the uh, chamber we are loading, let's say we are loading the wafers in the quad boat or crucible. It's made with that. Okay, then first nitrogen is flown, clean nitrogen for some time, then oxygen is flown. Okay, and once this oxidation is over, we again go for, to cool it, we again keep flowing N2 throughout the process. Okay, that is a typical oxidation recipe. And remember that we are not generally sticking to one kind of oxidation. It generally happens that we are using the combination of dry, wet, dry. Why? Because you saw that if we are, uh, let's say, let's say this is silicon, we want SiO2 this much, and we saw that the which one is better, which one is giving us better quality of SiO2, dry or wet? Yes, anyone?
Dries.
Dry is giving us better quality. Okay, but it has the problem that it is a slow process. Okay, so what is done is that generally the top layer and the interface layer, we want very good quality of oxide, because interface is the place where all the electrical conductivity and these things will be affected, as well as top we are going to use for further processing. Okay, so in general, dry, wet, dry is used. So top layer and bottom layer are made with the dry oxidation, and in between we are using wet oxidation, that is faster process. Okay, there is another way, another alternative of oxidation, that suppose that we are just trying to go for passivation of the layer. There we can grow n- silicon nitride. Okay, silicon nitride is also a common uh, passivating agent or passivating material that is used and can sometimes be used for some purposes where we are using SiO2. This is grown with ammonia. Okay, or we can even go for anodic oxidation for thick layers or like materials like gallium arsenide and all. Okay, so basic is oxidation we know. In case we are going for silicon nitride, it will be a similar kind of setup but with ammonia. And in case of anodic oxidation, there uh, electric current will also be used, anode and cathode, and as well as the reaction will take place as anode. So the wafers will act as the anode, and then we are using electric discharge to create the to do the oxidation of in such cases. In all these cases, purity, contamination control, and reproducibility are very important. We have to ensure that there is no contamination, no other material is used. Like if we are using oxygen, should be very clean, very pure. Nitrogen clean, and it should be reproducible. It should not be that I am doing it today at these parameters, but tomorrow if you do the same thing, you should get the same thing. You should not get something else. Okay, then we can say that this method is fine and we are able to reproduce it. Okay, clear till here? Any questions? Yes, anyone? Okay, now let's come to defects in interface. I am audible?
Yes, sir.
Okay, so now let's come to defects in interface. Now we have seen that we are growing on Si, we are growing SiO2. Okay, so there is an interface between Si and SiO2. Okay, so due to this growth of, just like we saw that while doping using diffusion or ion implantation, we were uh, creating some disturbances in the crystal. Similar to that, since here also we are growing the oxide from silicon itself, it will create some defects at the interface. Okay, and there can be four type of such defects, and these defects will play important role in our device. Okay, so there can be four type of defects. One is fixed oxide charge, represented by QF. Second one is interface trap charge, represented by QIT. Bulk oxide defect, or positive or negative trap charge, where charges are trapped. Okay, and mobile ionic charges like sodium or potassium. These can, if they have come in our like either they were present in our wafer or due to some contamination they have, like they have reached the interface, they can make mobile ionic charges. So how this field oxide charge origins? When the diffusion of silicon occurs in silicon dioxide. So ideally it should be neatly separated, Si, SiO2. But sometimes silicon can diffuse a bit inside SiO2. Okay. In this case, the the ratio of silicon, the crystal ratio of the silicon will get non-stoichiometric. Okay, near the interface. And so, how can we mitigate this? How can we control this or remove this? First is post-oxidation anneal in an inert atmosphere. That is, like you saw that we were saying that once oxygen is out, we keep on annealing it for some time with nitrogen. This gives us a better interface and lower fixed oxide charge. Okay. Uh, yeah. Then is maintaining the proper temperature and ambience for pressure and all these things will also lead in lower fixed oxide charge. Then third is orientation dependence. Like we have seen in the first class that we have 100, 111 or 110 silicon. Okay. In general, we are dealing with 100 and 111 uh, silicon wafers. Okay. When we are growing, in case of 100 surfaces, the defects are lower. If, if we have a 100 wafer and the interface is forming there. Whereas in case of 111, the defects are more. Okay. So we can avoid 111, but in case where you need 111, then you will have to rely more on the post oxidation and dealing with it with temperature and ambience, like that will play more important roles. But by default, if you are using 100, that will have lower fixed oxide charges. Okay. Then second type of defect is interface trap charges. Okay. These are due to the dangling bond at the silicon interface. Because now some silicon has been consumed in forming SiO2, some mid-gap defects can occur due to the unsatisfied valencies. Okay. And how it can be tackled? It is tackled by using forming gas. Forming gas is the mixture of hydrogen and nitrogen. A mixture of hydrogen gas and nitrogen gas. So after all this oxidation has been done, some nitrogen flow for some time, forming gas anneal mixture of hydrogen and nitrogen gas, that is the forming gas, is given to the chamber and then it is annealed. So what hydrogen does is that it passivates the dangling bond by forming silicon hydrogen bonds. That, and it has to be done as the last high temperature step. If some other high temperature steps are done after this, again interface trap charges can occur. Okay, so this has to be done at the last. Then is bulk oxide and mobile ionic charges. Okay, these are due to broken or unsatisfied silicon oxygen bonds in amorphous silicon dioxide. So till now we were talking about what are the problems in silicon. Okay, but there can be something from some problem in SiO2 also, like some unsatisfied bond of silicon oxide. Okay, then some positive or negative charges, like I was saying, some potassium, chlorine, any such ion can occur. Okay, in case of mobile ionic charge and halogenic oxidation, like HCl or chlorine gas, this can be used to remove mobile ions. But the first and the best way is to minimize sodium, potassium, and this thing at first only. And if we are going for HCl or chlorine gas to remove the mobile ions, in this case, it has to be done very safely because this is highly volatile and corrosive in nature. Right? Now let's come to, if we have grown the oxide, how will we know that the oxide has been grown and how much it has been grown? There are some characterization techniques. Yeah. Are you able to see my slide?
Yes, sir.
Okay. So what are the techniques that we use to, to measure the amount of SiO2 grown? In this case, unlike the doping, where someone was asking that is there any physical change or not? In case of silicon oxide growth, there is physical change you can see. The color will change. It will become a bit dark bluish in color. Okay. First thing is by seeing that only you will know. And in fact, if you see, if you are like continuously seeing these wafers, by seeing the color reflection, also you will get a approximate idea how much of oxide growth has been there. Because as the thickness will increase or decrease, the reflected color will also change a bit. Okay. So the first way is ellipsometry, in which it is the wafer is kept in like SiO2 is uh, glassy, like almost transparent. It will have some refractive index. Okay. So it will uh, the light is kept and then it is refracted and it will go back. Silicon is reflective, SiO2 is refractive. Okay. Based on this, it will know like based on this technique, that is ellipsometry. This is the most common technique used to determine the thickness of SiO2. That is used for to determine the thickness based on the film density, because SiO2 have some fixed refractive index, and how much the light traveled and uh, how well it is refracted. Based on that, we know how much is the thickness of the SiO2. Second is profilometry. In this case, a simple stylus, that is a tip kind of structure, will move over the, suppose that SiO2 is grown here. This method is more useful if you have difference in profiles. If you have a complete uniform profile, it will not lead to, it will not be of any use. Here you will have to create a difference. So either you are covering it with something, some part is to be oxidized, some has not to be oxidized. In that case, profilometry is used. So this will move close to this, like, and based on the pattern that it touched, it will determine that it will give you the graph, and you will know that what was the base thickness. If you consider this 0 and this is say 1.2 micrometer, so you know that 1.2 micrometer is the thickness of the film that we grow in one part. Other part it was not there. Okay. Then there are X-ray reflection techniques that gives surface roughness and density measurement. So once you have done this, you will go for confirming that whether you have done on what is the output that we are getting, is it correct or not. Then we can go for TEM or SEM, that will give us the cross-sectional analysis of morphology, dislocation, stacking fault, all these molecular level things we can see, as well as AFM is used to determine the surface roughness and morphology. Fine. Any questions still here? Yes, anyone? You can unmute and speak if you want.
Uh, just this measurements right now, the technology is well matured, sir. Like we will get the exact details of how much SiO2 is grown on the film.
Exact details, like you cannot say that everything will be so precise, right? So certainly there will be some error factor, plus minus. Like ellipsometry is having some error, but if you are going for TEM or SEM, you will get much precision. But that will require like creating vacuum and like taking time, as well as you will have to go to specialized center. These are like ellipsometry is a small instrument, just this size. Okay, and TEM and SEM, you have a complete setup. It has to be done in a proper like proper place where it has to be kept everything. So based on that, so some techniques like ellipsometry is the most common and the fastest technique we use. Okay, to determine. But if you want very precise one, then you will have to go to TEM, SEM, or AFM. AFM will anyway not tell the thickness; it will tell the surface roughness, and that also like high quality AFMs are there, which will give you roughness in terms of nanometers also. Fine. Any other questions?
Okay, sir. Thank you.
Yeah. Okay. So now let's move to questions, and I hope you all will answer. Okay. First, we will discuss with. Let's start with problem one. Due to backscattering of lighter ions, the skew in the concentration versus depth profile will be towards surface, bulk, interface, or defects. Remember, it is backscattering of lighter ion. We are talking about ion implantation, right? Okay, yes. Any answers for this? I think we have discussed this today only at the starting. Yes,
Surface, I think, sir, like moving on the
surface. Yes.
shifting to the
Any?
left side,
Yes,
like
left.
left side.
Yes. So that is the surface. We are representing surface, then going deep, right? Yes. Any other answers? It is surface because when lighter atoms like boron hit heavier atoms in the substrate, that is silicon, okay, they are reflected back towards the surface. This results in higher concentration of implanted ions near the surface. Okay, so the profile is not what we expect at the surface. Okay, which of the following gives uniform doping profile? Diffusion, ion implantation, thermal growth, or chemical vapor deposition?
Ion implantation.
Ion implantation. And why not thermal growth?
Thermal growth, I think temperature may not be uniform in all places of the wafer.
This is not a technique for doping. Thermal growth and chemical vapor deposition are not the technique for doping.
Okay, for
Yes.
deposition we use them, right?
Yeah. Yes. Beduduri, I am not getting your complete name. Bediduri Ganeshwar, right?
Yes, yes, yes.
Yeah, you were saying something.
No, I think those two are used for the deposition of the layers, I think.
Deposition. Yes, these are deposition technique. This is growth technique. This is deposition technique, and then we have physical vapor deposition also. That is deposition technique. So when we are talking about doping, it can be done by diffusion and ion implantation. So ideally, we are comparing between these two. And if we are saying that, then in case of ion implantation, we will get better doping profile. Okay. Diffusion creates gradient, like it is mostly flow of dopants by their own virtue, like due to the temperature they will flow. In case of ion implantation, we are putting at specific positions. Okay. Now let's come to one question where in amorphous silicon, this is not crystalline. Okay. Amorphous silicon, say for 10 to the power 18 per centimeter cube concentration of dopant, the RP equals to 15 nanometer. Find the dose required. What dose of uh, this will be used? to create this amorphous silicon with 50 nanometer RP. Yes, anyone? Oh, let's discuss that. The dose is concentration multiplied by RP. Okay, we have concentration as 10 to the power 18, and the RP is 50 nanometer. Okay, now this is centimeter, this is nanometer, so we'll convert 50 nanometer into centimeter. Okay, and then if we do the calculation, the dose required will be 10 into 10 to the power 12 per centimeter square. This dose will give us depth of like doping depth till 50 nanometer. Fine. Am I audible?
Yes, sir, Your Honor.
Okay. So let's move to problem 4. During implantation, the critical dose is the function of, I think it's not changing. It's changed. The slide have not changed or it's changed.
No, sir, it's not changed.
Okay, let me check
Yeah, no, it's
now.
changed.
Okay. During implantation, the critical dose is the function of pressure, substrate temperature, chamber temperature, or gas flow rate. How will, like, which factor will determine the dose?
Chamber
This
temperature?
is glass flow rate.
Gas flow rate, chamber temperature. Yes, any other answers? There can be multiple correct answers also, not an issue.
Sir, one of them energy also, right? Sir, energy like how much energy? Like, it's not there.
Yes,
I am thinking.
yeah,
How much?
energy is certainly the basis of ion implantation, right? So certainly it will play a role. Yes, any other answers? It is the temperature of the substrate.
Annealing rate, sir. Annealing rate.
Annealing. Yeah.
Yes.
So the critical dose for amorphization, okay, during the ion implantation. So a higher substrate temperature can help anneal out the damage. Okay. So this will determine the critical dose required for amorphization. So if we are doing the implantation at a higher temperature, it will have a higher critical dose. If we are doing at lower temperature, the critical dose will be less, like that will create more damage. Even a lower dose will create more damage.
Sir, substrate temperature means the temperature of the wafer, like how it is
Yes,
like.
of the wafer that can be heated.
Okay.
The whole,
Like it retains some temperature. Say in annealing, I heat this wafer. So inside there is a temperature inside that vapor. You mean to that substrate temperature
no,
means?
no, substrate is very thin, right? So the holder that is in all such cases, wherever we are talking about, until unless we are talking about like oxidation chambers and all, mostly if you are, even in case of PVD and this we will talk about, if we are talking about giving some substrate temperature, in that case the substrate is kept on some holder, right? That holder itself is heated. That there can be a heater below that holder, like a metal holder on which you are putting the wafer or fixing the wafer using some screw or some clips, you can say, and that the holder itself is getting heated because there is some heater put inside, heater with a temperature control. Fine.
Apart from that, there is a chamber temperature also, or this is the
Yes.
temperature we both
Now,
temperatures will be.
yeah, both temperature are different. If someone is talking about substrate temperature, that is the uh, the holder temperature, and if someone is talking about the chamber temperature, then the whole chamber is heated or the whole area is getting heated. Yes, you are saying
Sir,
something.
will
Yeah.
chamber temperature affect the ion implantation?
Yes, but chamber, you see, it is a very big setup. I think in the previous class I saw that ion implantation setup is not very small. It is big, like you can say a big hall is required for this ion implantation setup. So the starting point is this, it will go and it will then deflect and go. So this whole thing, na, it is very big. The whole thing cannot be heated. This whole area cannot be heated and maintained at such a high temperature. Practically, it is very costly, and I will say like that will increase the cost a much, like many times. So that is not a feasible solution that we can go for.
Sir, you said that substrate temperature will affect the process in a great manner. Can you explain
Yeah.
it in a better way? Like how it will
So
affect?
surface temperature, like if it is at a higher temperature, the crystal will like if there is some disorientation due to the ion implantation, that some ion is coming like phosphorus or boron, that will create some disturbance in the crystal. We have a crystalline silicon, right? So that is coming, and that will create some disturbance. But at higher temperature, you might be aware that the crystals have the property that like atoms have the property that they tend to align to their lattice position at higher temperature. Okay, due to
Yes,
this
sir.
property, they are like they are more likely to go back to their correct position, and the disturb like the surface damage is less. And after this also, that is why RTA is done, so that if they have moved and it is at a higher temperature, it will realign itself. What how much it is possible? Certainly, it will not get back to the perfect shape like it was at the beginning, but it will uh, orient itself. The atoms get enough energy for themselves to orient to correct positions. Fine.
Yes, sir.
Okay. Now let's come to problem 5, that is ion implantation process is compatible with yeah, with which of the following: high temperature, soft mass, isotropic profile. Soft mass, anisotropic profile, low temperature. High temperature, isotropic profile, hard mask, or hard mask, anisotropic profile, low temperature. Which one of these combinations is for ion implantation?
Option B.
B. Soft mask, anisotropic profile, and low temperature. We can do this process at low temperature. It does not require that much of temperature. Certainly, like to lessen the effect of this damage and all, we can go for temperature, and we can do some small RTA and this thing that will be much uh, less like that will not be for a longer period of time. So it is soft mass, anisotropic profile, and low temperature. And soft mask is, we can even use photoresist. It does not always require hard mask like SiO2. Thin SiO2 can also be used in some cases. Certainly, like that will be better than a photoresist, but even a photoresist can work well. Okay, and here it
Sir,
is yes,
other than hard SiO2 for hard mask, are there any other materials?
yes, silicon nitride is there. Most of the dielectric we are talking about we can use, but SiO2 is very common because SiO2 is the easiest to grow and it gives very good interface. Like SiO2 interface is said to be very good, and that is why SiO2 is very common.
Okay, sir.
Silicon nitride is also used, and in fact, when we talk about passivation and all, silicon nitride is preferred one compared to SiO2. Okay. Then we have anisotropic profile because here it is not like diffusion. We can make in one directional profiles. Okay. Next is wet oxidation is used for gate oxide, field oxide, passivation, tunnel oxide.
Field oxide.
Field oxide. And why not for gate oxide?
Gate oxide need it should be very thin and it should be very uniform.
Yes. So it should be ideally a good quality one. And we know that in case of wet oxidation, the quality is lower, right? So we cannot go for gate oxide for this. Whereas in case of field oxide, we can go for wet oxidation where we are just using it to shield it, or even for passivation also we can go for uh, no, we cannot go for wet oxidation for passivation. Why? Passivation also can be done can it be done using wet oxidation? It does not require very good quality, right? Yes, anyone?
Because of water and you mentioned passivation may cause some issues.
Okay. Yeah, Hari, you were saying something. Yeah, hello.
Isotropic is not, sir, isotropic in a particular area is not the reason.
Okay. See, when we are talking about passivation, we are generally covering metal and these things with oxide, right? And how can we grow if we have metal over silicon? So the silicon below will also get oxidized, right? So passivation is generally done. It can be done using oxide SiO2, but in that case, it is generally deposited. It is not grown. In the beginning, I said no, there can be some way that it is deposited. It's not all SiO2 is not always grown, but if it is grown, it is of better quality. It is best, but sometimes we have to deposit also. Fine.
But you're telling like passivation don't require high quality, sir. Why it is so? Because passivation is purpose is for the this environmental protection. No? So
Yes, it is just for protection. It does not have any role in like it has no electronic role. It does not play any role in electronics. It is just to cover. It it can be if you want to cover better, you can make it thick. There is no issue with this. That if there are some lattice damages and all, right? But whereas if you are talking about gate oxide, it has to be very good quality so that it is reproducible. Like it should not behave abruptly. If I am making gate oxide 10 nanometer and I have said that 10 nano 10 nanometer gate oxide should give this dielectric constant and these things. 5 days later, if someone checks it, it should give us something similar, right? So there should be less imperfections. That is why we are saying that it should be of good quality. Whereas uh, places where we have the purpose of like protection and these things, but we don't need very precise uniformity and these things. So we can say that even a low quality or not very low quality, but wet oxide, wet oxidation can also work for us. Like I said, na, that at interfaces we might need good, maybe on top and bottom. We are in need of better quality because bottom it is the interface bit from silicon and SiO2, and top this is where we will further do some processes. Like in case of sensors, okay, if you are making a sensor, you are not going for this. You are not making some processor or something. Sensors, they are mostly made on SiO2. You take silicon, grow SiO2 over it, and then make silicon. So basically, you just need a insulator below. Fine. So in this case, do the quality of insulator below will determine anything. We just need an insulator. It don't have any role in our circuit. Okay.
Not
In that
that much, maybe. Yeah.
yeah, yeah, that will not play much role. Yes, if it is of very good quality, not an issue. But even a bit lower quality will not affect us, right? So, if you are, say, if for a very good dry oxidation, complete dry oxidation, 2 micrometer thickness, you are getting, and the cost is say 8,000, and when you are going for the 2 micrometer with dry wet dry, and the cost is, I am saying approx, okay, and the cost is around 5,000. Which one will you go for? If your purpose is just to make sensor.
5,001.
5,001, certainly. So cost also plays a role. Cost time and cost increases because the time is has increased. The time for processing has increased. So these factors are very important when we are considering what kind of oxidation process for which purpose. And in case of gate oxide, if we go for wet oxidation, yes, you are saying something.
Sir, can you please give clarity on why we can't use wet oxide for passivation tunnel oxide?
Uh, as I said that you can use if you have a blank wafer. Okay, you have a blank silicon wafer, you do oxidation, and it's fine. But in that case, you will not be doing passivation. Passivation is when you have made the circuit, say you have some metal contacts here, 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 and then you are covering these parts except for pads. Okay, everything you are covering with something. So when you want to cover it above metal, can you do oxidation of metal to make SiO2?
No, sir, can't do that.
No. Yeah, that is the thing that yes, silicon oxide can be used for passivation, but it will not be grown. It will not be grown using wet oxidation. It will be deposited either using some CVD methods or in general some PVD methods like sputtering. Fine.
So then tell about the tunnel oxide also, please.
Tunnel oxide also like it will be deposited, and you cannot make if you have tunnel like whenever you need tunneling, you we have seen that oxidation will actually consume like if it is consuming 45 like whatever the volume output will be there, it will be 2.19 times the actual one. Okay, so the tunnel will be blocked if you go for oxidation. If you have created some MEMS tunnel and these things, in that case, the dimensions will shrink. So we cannot directly go for oxidation in that case.
Okay, sir.
Okay, now let's come to problem 7. That is, if the diffusion of oxygen is faster than H2O, why is the growth rate faster for H2O?
Sir, option A.
Option A, that is higher solid solubility and higher availability of oxygen species. Any other answers? Oxygen, despite having a higher diffusion rate, okay, has lower solid solubility compared to H2O, okay, in SiO2, and thus has higher availability. Okay, this leads to faster growth rate because as we saw that H2O is smaller molecule, so it will have higher solid solubility. That means, in a sense, it will be like higher solid diffusibility compared to oxygen. Whereas if we are talking about diffusion rate in normal condition, the oxygen molecules have higher diffusion rate compared to H2O. The reactor tube used in oxidation furnace is made up of glass, quartz, polypropylene, or tungsten.
Quartz.
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 Yes, because we are going to very high temperature of 1000 degrees Celsius, and glass will not work, polypropylene will not work, tungsten will also tend to like not work there. Which precursor is used to deposit silicon nitride? Nitrogen at 500 degrees Celsius, ammonia 1000 degrees Celsius, ammonia 800 degrees Celsius, nitrogen 1400 degrees Celsius.
Option C.
C,
Ammonia.
that is ammonia at 800 degrees Celsius is not used, but 1000 degrees Celsius is used.
Yeah, 1000.
1000. The temperature ammonia is the correct answer, but at 1000 degrees Celsius is used to make silicon nitride. Okay, and this is one of the very common passivation agent. Okay, it is mostly used for passivating. Okay, even nitrogen is used. Directly, nitrogen can also be used, but it will require higher temperature. It is very similar to what we are saying that H2O and O2. Okay, because if we are directly using O2, we are doing it at a slower rate. If we are using H2O, it is at higher rate. In case of silicon nitride, if we are doing with ammonia, a lower temperature is needed compared to nitrogen if we are doing with direct nitrogen, because breaking the nitrogen molecule to make Si3 and 4 will be difficult. Like that energy required is higher compared to the energy required to break the ammonia molecule. Fine.
So just a question of operation. When you're
Yeah.
sending the ammonia to make the deposit, are you doing any treatment to the ammonia to break the N ions and H3 ions, or it will be directly sent to the wafer? How it is?
See, if uh, it is mostly temperature dependent. Molecules, when they get enough energy, they tend to break. Like when the activation energy is reached, they tend to break and do some reactions, right? So we are not breaking it outside, but due to the temperature itself, this reaction occurs.
Okay, it happens because of temperature automatically.
Temperature. Yeah, that is why you see the answer C is not correct. Because if you are doing it at 800 degrees Celsius, you will do everything correct, but the activation energy will not be enough to break the molecules and for this reaction of silicon and nitrogen to happen. Temperature plays a very important role. Okay, now let's come to the next question. Which of the following defects can be reduced using forming gas anneal? Fixed oxide charge, oxide trap charge, interface trap charge, or mobile ionic charge? Forming gas. Remember we talked some time
Yeah.
back.
QF, sir, fixed oxide charge.
Fixed oxide charge. Yes. Any other answers? Yes. Anyone? It is the interface trap charges. It is a mixture of hydrogen and nitrogen, and this reduces the interface trap charges. And how it does? It does by passivating the dangling bonds at the silicon dioxide interface. And remember, whenever you are doing this process, it has to be the last high temperature process. After this, the wafer have to be cooled down. It should not it should not be followed by some other high temperature uh, processes. Right? Yes. Any other questions?
Sir, that assignment to problem one, that
Assignment
diffusion
two.
curve.
Okay. You have that question with you, or should I take it out?
I should take it out from the website, sir.
Okay. Let me check. Just a minute. Just a minute. I am also taking out the question. That is week 2, problem 1, right?
Yes, sir. Yes, sir.
In a 100 nanometer thick silicon dioxide layer, if a 100 nanometer reduces the diffusion coefficient of phosphorus in silicon for a process time of 1 hour.
I think it's related to diffusion charge or something.
Yeah. The deadline is over.
Yes, sir. It's
Okay.
over.
Yeah, because I cannot discuss before the deadline is over, right?
Actually, the issue is there are so many formulas in the book to
Mm.
calculate this thing. So even I was confused that which formula should be used.
Yeah. So, what is the formula for diffusion depth? Hello.
Uh,
Square root of dp into
Yeah.
t.
So, can I draw here? Yeah. So let's say x equals to under root, yeah, under root dt. Okay. X is the diffusion depth, d is the diffusion coefficient, and t is the time. Fine.
Yes, sir.
So, what are the initial conditions? We have d was given. I think I should take one blank. Right. Just a minute. add one slide here. Hmm. Okay, let's write it again. Okay, so hello, am I audible?
Yes, sir.
Okay, so say x equals to under root dt. D is the diffusion coefficient, T is the time, X is the diffusion depth, right? So what is given here is that T dash equals to 10 to the power minus 14. Am I doing it right? If I am missing some numbers, you can say. Okay. So 10 to the power minus 14 centimeters square per second. And the time taken T equals to D dash y I am taking because there is change, right? So reduce if I layer reduces diffusion. Okay. ठीक. So the standard one is this. Okay. Time we are taking as 1 hour. And if we convert it into seconds, how much it will be?
3,600 seconds.
3600 seconds. Okay. So now the diffusion depth at first is T dash into T, right? So 10 to the power minus 14 centimeters square per second into 3600 seconds, right? So if we calculate this, how much we are getting? 10 to the power 12, it will minus 12, 3.6, 3. So how much this is? X equals to
Is it
under root
6
30,
into 10
yeah,
power
36, let's say 36 into 10 to the power, this one, 10 to the power minus 12, right?
minus? Yeah, yeah.
Centimeter square. And if we say 36, under root 36 is 6, and 10 to the power minus 2 will give us 10 to the power,
10 into 10 power minus 6, I think, no? Minus 6,
yeah, minus 6,
yeah,
okay?
centimeter square.
Centimeter because square is,
Centimeter. Yeah,
yeah,
correct. Depth, right? Yeah.
yeah,
Okay.
okay. So this one gives us how much in, if it is in centimeter, so in
10,
in terms of nanometer, how much it will be?
0.6 nanometer, is it?
So they asked in micrometers, sir.
Okay. So
The
10 power
answer is in
minus 6.
micrometers, right? Yeah. So if we
So
convert it, it is 6 uh, into 10 to centimeter itself is 10 to the power minus 2, right?
Minus 2. Yeah, yeah.
So we can say 0.0
0.06 this
micrometer.
micrometer.
sir,
New
That
but they
is
gave answer as 600, sir.
600 nanometer is the answer.
yeah.
Sir, but they asked in the micrometers, sir, in the question.
Oh, is okay. And type numerical. Okay, acceptance. Okay, that is the issue. So for this also, you see, like this is being monitored. Like the TA is responsible for the questions, and this they are different than me. Okay, so for this, you will just have to raise a query in the discussion forum. Okay,
Okay, okay.
yeah, just raise a query in the discussion forum so that they can respond to it. That is simply a minor, like unit error, right?
Yes, sir, yes, sir.
Yeah, that will be done.
So generally in semiconductor industry, which unit system is followed, like SI unit, or is there any standards like generally?
Yes, there are some standards, but you see, most of the uh, things depend on where the fab is. The starting fabs were mostly Intel, Motorola, and these things. They use the US standards, that is the metric system, right?
Inches like that.
Yeah, inches and this. That's why you see the wafers are still in inches. 3 inch, 2 inch, 4 inch, 8 inch, 6 inch, 12 inch, like that. Okay. So many times you will see things in metric terms because mostly the fabs were located in US when they started. Now we have fabs in many Asian countries like Taiwan, China, and South Korea also. But yet, most of the same standards are followed. But somewhere you find like when we are talking in sense of like thickness and all, inches, seconds, and minutes, that is very difficult. So we go for nanometer. So it's a mix. You have to take care of both these things.
In research, sir, like when you want to publish paper in that way, generally,
It
there also.
simply depends on like if you are going to publish something in IEEE that uses the standard like international standards, that is the normal system we use. And if you are going to publish in case of say specifically some American journals say it says that no, we want in metric system, then go for metric system. Otherwise, international system is well accepted everywhere. There is no such restriction, but yes, sometimes we need to understand that yes, what it is. It is just that you should be aware that what is an inch. We cannot say that we don't know because something can be in inches also. Like you see, uh, standard one is meter, but here we are using centimeter because it is more convenient. Fine?
Yes, sir. I have another question.
Yeah,
Actually, yeah, if it is very amateur question, I'm very sorry. I'm
not an
just
issue.
understanding how it will be in the practicality. Say, for example, we have a one topography of the IC circuit. Okay.
Mhm,
So
mhm.
you have a wafer on that. You want to deposit some other materials, which will goes like a lines or maybe that line topography or something. So
Mhm.
in that lines, are we using this silicon dioxide, or below that lines we are using the silicon dioxide when we are growing the native films? Like generally, how it will be?
Generally, it will be that you start with a blank wafer, nothing is made over it, like a wafer, and then you grow oxide over it, so complete oxide. And then whatever pattern you want, like you want that the oxide will be removed from this area. This area we have to do something, then this area again we have to remove oxide we want to get to the silicon. And here, okay, so we will create a mask that will cover all other areas, just leaving these areas open. Okay,
Okay.
you will learn about lithography process and all. Okay, we will create something that will cover all other areas and remove just keep this area open, and then we will dip into some etchant. It's generally for this dilute HF. Okay, that will remove the oxide from that area.
Okay. Okay. So
So
generally, if we see the topography, the metal, the lines are not metals. You mean to say they it can
no,
be?
after this there will like if you say about a normal like processor or something, there are not just 1 2 steps, but around 200 300 steps to
Oh,
achieve
okay.
that. Many materials are deposited, many metal lines are deposited. Those are metal lines, but when you see like gold kind of things, right? That is gold only. Those are
Okay, sir.
metal lines. Yeah. So after this, further processing will be done. This is the starting
Okay, so various things are there in accordance with our required device. So it
requirement.
is
Yeah.
not like a standard process or something. Yeah.
Yeah. And you have to plan like just making a circuit, that's fine. But you when you are going for fabricating it, you have to plan each and every step, like how many steps you have to reduce the number of steps, as well as you have to achieve all the things. So in that case also, this whole field becomes quite fascinating.
Yes, sir. Because what I had understood based on the field is it's not like every time same thing you do. So every time
Yeah,
different requirements or
different
different
requirements. Yeah,
process. So
and
that's
every process requires a lot of optimization. It's not
yeah.
that it is written somewhere in a book and you do it. You will even it happens that in one season the same parameters were working, the season changed and the parameters changed because some factors which we might not be considering have changed.
Yeah. So the industry might be evergreening, sir. Then, matlab. So there
Yeah,
are yeah.
it's like that. Yeah. So in the next week, the topic is additive manufacturing, that is chemical vapor deposition. That will be covered in the next week. And someone was having the question that the questions of this chemical vapor deposition are asked in week 3, right? That you will have to post in the discussion forum. Okay. So
Yeah. One
that's
more
all
question,
for,
sir.
yeah, yeah,
Sorry.
sure. Yeah, yeah,
Sorry, I'm asking some questions.
yeah, no
In
problem.
many times, the bottleneck things are discussed in the course. Like I read this one.
Yeah.
So bottleneck means it's a general word, or it has a common understanding in every
No,
in
that's
many
general word, like
general word.
English
Okay,
word. Yeah.
understood.
Yeah. So thank
Thanks,
you
sir.
all. Yeah.
Yeah.
See you in the next class. Thank you.
Yeah. Good night, all of you. Thank you.